right? We're computer scientists, we deal with exponentials all the time, but when they get very large, even our intuitions get a little muddy, right? Intuitively, you may have thought, well, you need some kind of unit there because it makes a difference. Does it? No, it doesn't. One more space one, because I like space. Space is cool because lots of things happen, unless you're modern America. Speed of light, constant, right? Again, asterisk, but we're just going to say it's fixed. Big Bang. Anybody not believe in the Big Bang? It'd be perfectly okay because it doesn't matter. This is just a thought experiment. At one point, it was the size of a molecule. Okay? And then in 10 to the minus 36 seconds, we'll come back to what the significance of that number is. It grew to the size of the Milky Way galaxy. If you don't already know, the speed of light is much less than it would take to grow in that amount of time. So how did it happen? Can anybody guess how you could keep the speed of light fixed, the same, constant, yet grow that fast in that short of time? Yeah, you're kind of thinking in the right area. You're trying to screw with other things, right? Because you can't mess with C. You're trying to figure out... Yeah, still getting there. It's actually a lot simpler. Asterisk. I'm not a physicist. I will not be able to explain this mathematically. Because it starts having lots of the fun constants, which, that's just upside down V to me. If two people are, how many people have been to the airport? You know the, I don't know what you call them, but escalators that go horizontally? What are they called? Moving walkways. Okay, great. If I have two people and they walk away from each other at the same kind of speed, but then if I put them on those moving walkways that move a fixed speed, how fast would they be moving away from each other?
Twice that speed?
Non-linearly, right? If I'm walking away on that thing, I'm accelerating away. Because you can kind of think of it, I'm injecting space into every little point. Another way to think of it would be like a fish tank. You've got two fish in it, infinity fish. And I have pumps at the bottom of this thing and on the side of this thing. And these fish swim away from each other at the same speed, but now I inject water into this tank. So there's constantly more space in between them at every little point. Is that starting to make more sense now? That if I'm putting stuff in between us and we're walking away, how fast are we moving away from each other? Non-linearly. Because everything's growing around us at every point. So in this model, if we go back, the speed of light was the same, but the amount of space was increasing everywhere. Space was getting larger at every little point. If I draw this and I start growing them all, you may have seen diagrams like this before. Think cellular biology, like little petri dishes and they all start growing, kind of that effect. And apparently you can prove that all with math, but who cares? It's more fun just to think about it. One more? Yeah. This stuff is actually equally important to the talk. Chaz, you already know the answer to this. Chaz got to cheat a little bit, so I'm going to force him to be quiet. Two programs. Which one's simpler? A program that can store an arbitrary integer. Okay? So I could put 1 in here. I could put 1,000,000 in there. I could put a very, very large number. I don't want to say infinity. It's finite, though. It has to be representable. And then over here, I have a program that prints 1 through all the integers. Okay, so I start running it. It has little print statements. It says 1, 2, 3, 4, 5, on to infinity. This one simply prints out a singular number. Which one's simpler? In the context of simple, which one takes less time to run? Actually, I'll restrict it even more. Which one compiles faster? Let's think about that. if this is a very huge number, actually, you know what? I had a huge number from before, right? How long will it take to represent that in memory? Quite a long time. Will it ever finish compiling? It's constantly in there trying to represent that in binary or something, so it just kind of goes on forever. How long would it take to compile a program that is only this? While true, print I being 1, and then increment I. It takes a fraction of a second to compile that, and I can instantly start running it. How long will it take before it gets to this number? A very long time. This one never finishes compiling. So in a sense, it's simpler to represent every number than it is to represent a particular number. So, kind of alluding to things, this is an ensemble. Over here we have the ensemble of integers. Over here we just have a singular element. And what I've just told you, that it's easier to represent all these guys than it is to try and pick an arbitrary one out and represent it. It's kind of glossing over the print statement. It's our magic print statement. It takes no time to print. Okay, anybody learn anything there? Party tricks to impress your friends? Isn't that all that a CS degree is? Yes, in a sense. Okay, let's get back to OO. So this is the thing that we're most comfortable with. At least we think we are most comfortable with. Let's test how comfortable we really are with it. Emphasis on this is creating classes and deriving an object, right? We're very used to this idea. The emphasis then on the object is then the interaction of objects, right? So if you have an array list of people inside a city class, it's the interactions of array list to city. It's all of how you place these objects around. I'm skipping the hard definition of OO, saying like you want to decouple your objects and all that. The way I would think of that, here we go, drawing time. If we have objects A and we have objects B, the way I think of the interaction in OO systems is that even though you're trying to decouple systems, and they always say that, like in 335, I heard decoupling, decouple, and I never saw what decoupling was. So I've kind of created this very disgusting monster in my mind that maybe helped me look at things a little differently. I don't know. In my mind, they're kind of like this. You're always like smashing your objects together, smashing your classes together, right? You have a class that implements something. This is the implements logic here. If you have a class that has a relationship, well, that's the smashing right there. That's the overlap. And what we want to get to is where we can talk about things in separate groups completely. And instead of focusing on how we smash objects together, we focus on maybe functions in between them. What's the significance of this? Well, instead of working with singular objects, now I can kind of represent these as very large groups of things and not really care so much about what they are. What I start to care about is how do I do interesting things on them. How many people ever thought of functions this way? Slightly, right? How about in terms of your degree? How often did you think of things in that way? Probably not. Because what you were more concerned with was maybe methods on objects, right? Always within yourself. You have an A, methods on A, right? Call methods. Okay. Let's get to the fun now. I see we have a couple functional programmers in the audience, so for people that haven't taken functional programming, it's going to be very easy because the emphasis on those classes is not right. Not right, asterisk. It's correct in how it's presented, but it misses a lot of very interesting things. So let's talk about the interesting things it misses. Because right, we're kind of told that like functional programming is awesome, that you can program with functions, is that any different than what we've just been doing? Functional programming, emphasis on functions. Python has first-class functions. Is Python a functional language? Yeah, I mean, it depends, right? Yeah, it really depends. If your definition of functional programming is first-class functions, then Python fits the bill. Does Java fit the bill?
Java 8?
Yeah, Java 8 does, so we've heard. Does Java 7?
No.
No, not in the sense. You could use an anonymous class and fake it. Then it's kind of like, what's the difference? There's subtle differences. You can fake those too. So at what point do you just say, like, no, we're done? That's not functional programming. But clearly what I'm getting at is we're not making a very good case for functional programming at the moment. We're just saying we get an extra kind of data type, right? You get a function now. How many people are familiar with OCaml or SML, ML, these kinds of languages? Okay. For everybody that's not, OCaml is supposed to be a functional language like Haskell that we teach in 372. Why did they not get this ensemble thing? They have first-class functions, and well, we even call them a functional language. So what was the breakdown there? It turns out to be a very subtle thing that Haskell just magically got right. And it forced them to think in such a way that they kind of arrived at this thinking in ensembles, which is still this kind of cloudy thing in our mind that we're trying to get to. Let's look at a simple program. And print x. Okay, simple enough, right? What am I missing? Semicolons. Some of your eyes might be lighting up at this point. I'll still try and make it interesting. Is this functional programming, or is it OO programming at this point? Do you not have enough information to say one way or the other? Probably that, right? I could say this is an instance of a class. I could also just call it a function. What's the difference? What we're concerned with is how we operate between these functions. So you can see we're passing data. In most languages, this would just be perfectly fine. We would not consider this functional programming at this point. We would consider this structured or stateful. I call it semicolon programming, statement-based, right? I could define the functions, but it wouldn't matter as much. But I'm going to introduce a slightly different syntax for representing this to kind of stretch this out. We have f of 1, and we're interested in what it returns. So the whole idea behind a function is that you give it one input, you get one output. This is very simple. It's a lot better than it gives arbitrary inputs, returns, whatever it wants. That would be a really crappy function, right? You use it one time, it's a little different. Here we're going to stay very simple. Its return value is an x. But I don't want to confuse anybody and think that it's this particular x. So I'm going to say it's the return x. I'll just say it's Rx. So it returns something that will be labeled X. And this we give it an actual name. So maybe int X. From here we produce, I should say, we get a g of x. And what's g of x's return? We don't know. We haven't. We're saying that functions have to return something, right? So let's just give it a value. We'll call it ry. And then we'll do our print statement. Print x. And let's go ahead and elevate that to a function. Close enough, call it good. Okay, now in this model, what has changed? Our g of x is what we're concerned with because it's void. And this is where this always breaks down in functional programs. If you've done functional programming, there's no concept of a void function. Let's not worry about unit. Unit is heavily retarded. In my program here, if I have access to x, and I feed it into g, that's perfectly fine. It's scoped, it's available to there. And in g, we're not going to use its result. So what can we do with it? We can just ignore it at that point, right? So we'll denote that with just an underscore. we throw away its result. And then we ask to print something. Where is its x located at? Well, it was back up here, which is still in scope because we returned it. And what we folded this program into is from looking at it like this, where its statements, so line 1, line 2, line 3, we've looked at it, we've kind of flattened it out into this one-dimensional, well, they're both one-dimensional, but we've gone out horizontally at this point. We've kind of pulled it out, stringified it out in one direction. And we still have access to all our variables. We get a return value here, we happen to name it x. We need the x down here, but that's perfectly fine because it's accessible all after the right-hand side at this point. So if we had a function up here that depended on x, we'll call it f1, it wouldn't have access to this x yet. So kind of like time is always flowing in one direction, if you're human-sized, same thing goes here. You make an x, you can only use it into the future. You can't like go back in time. That would be an interesting programming model that can subtly exist in Haskell, interestingly enough, just by odd manipulation. But we're not going to worry about flowing backwards because my brain doesn't flow backwards, so we're only going forward. So how does this get us closer to the ensemble idea here? Hopefully this kind of brings everything together at this point. If these were classes, objects, functions, we didn't care. So these are the elements of some ensemble, which is what we're very used to, a person, class, et cetera, et cetera. What's the ensemble in this? What's the thing that's unique to every, or similar on every line?
Semicolon?
It's looking you right in the face. It's a semicolon. All this stuff changes, right? This all changes, but what's always the same? It's always the semicolon. So for the mind-bending thing, what is the ensemble in a program that's imperative, top-down, what you're used to? It's actually the semicolon ensemble. Kind of an odd thing, right? You probably always just thought those ended lines. You never really took the time to think about, like, what's the significance of the semicolon? It's actually the group ensemble. Haskell encountered this, and they were forced to deal with it in this kind of a context. And when they did, they saw that F and G don't matter. Returns are kind of blah. There's two types of them, right? We have one that captures its return. It says, I will assign you, I will let you be X in this program. And then you've got this other concept of, well, I don't care what you returned. I'm just going to keep going down on my computations. What do we get for free out of this? The notion of void. That's a void return, right? If it returns a value and I don't care about it, it's as good as void, right? Why not? How many people have encountered monads? A couple? And you're kind of like shaky on them? Who thinks they know what monads are? Don't be bashful. I won't say anything. This is your monad right here. Your semicolon is your monad. Okay? This one gets abstracted into something called do notation. And it also gets abstracted into these operators bind. But the interesting one comes from the other guys that actually have names. So if you've ever encountered monads before, you encountered things like maybe. Is maybe one thing? Well, no. So this is more like for the technical side, but it's always maybe and then parameterized by some value, right? A monad is not a thing. It's a group of things. It can vary on what it's parameterized over. So if you have a state monad, what state is it? Is it a program state? No, it's a generic state. What's another monad? Identity, that's an interesting one. Identity, it sounds singular, right? The identity. So in integers, we have 0 as our identity. Well, in our ring, right? For addition. That's when we get our identity. Identity monad, singular or not? Well, what's the identity of integers? And under something, 0. It's not a singular identity. It's the identity of whatever you're parameterizing over. So this concept of monads that you all are now familiar with, even though you didn't realize it, if you've ever had trouble with them, or you ever encounter them in practice or in your future, you'll now not think of them as a singular thing. And what has our education been trying to tell us this entire time? Right, we get, good Lord, what dimension am I looking at? Don't think and draw in your dimension. Could you imagine if that was 4D? We go through computer science and we kind of start forgetting. We start with 127, 227, right? And we know nothing. And we take a lot of things for granted. And that's actually the better way to look at the world. Then we get to maybe the 300 level classes, and at that point we know what an object is, right? I know what an object is. It's this. With these things, what you want to roll back to is, I don't know exactly what it is. I'm more concerned with, I've got two of some things, and I don't really care what they are. I just care about applying things into them. If you look, if I had a longer board and I didn't have to constantly erase, when I had this thing all drawn out here with the F's and G's and all that, I didn't care what the F's and G's were. I could swap those for all I care. Of course, that would change my quasi-type signature of void, but I wasn't concerned with the objects in that. I was concerned with how they were chained together. Okay? That's what we're going towards. So we have lots of things of B, lots of things of A. I don't care about how I sequence them together in the object-oriented sense, where I'm kind of saying, well, this depends on this and such in here. I'm more concentrating on trying to get out to this magical land of where I can get back to functions just running over things, and then let the monads be concerned with their details. In the semicolon monad, what we got out of that was the sequencing, right? Do F first, then G, then do the print statement. We got that for free. Anybody learn anything from that? It should be very hazy, and that's actually the idea, because I gave this talk in a more particular sense a year ago. And I tried to explain what monads were by showing what's called the writer monad, and what else did I do?
A year ago.
Well, it was over a year ago.
Sounds like it, yeah.
I think you did I/O.
That was the first.
Did you do
like,
I/O?
piece.
Did a little bit of I/O, so I'll just make it up because it doesn't matter actually. And that's what I'm trying to get at, is that picking one out isn't the significant thing. So we did I/O, we did writer, and writer's a really great example of how to construct these things in terms of Haskell. And what I'm trying to show here is that they're not things. It's not the writer monad. It's a group of things that act like writers. And then you can apply functions over them, but they don't care. In the similar sense of when we write imperative kind of programming, we're doing the semicolon monad, and we're applying functions onto that. And what we get out of this for free is that all our functions, when applied in a particular order, will happen in that order. You've been doing this for quite some time. You might have not even noticed it. What's another non-monadic sequencing that's in mathematics? Does that sequence things? It has to sequence things, right? It would be very sad when it doesn't. And it's actually interesting to look at systems where these become, when they commute, and it gets weird. We may hit that at the end. It came up on the 433 exam, and it was a really great question. I heard it from one of the students. But in here, we have to run G first, then we have to run F. If we flip these just willy-nilly, we can't agree, we can't assume that that'll be equivalent. So we can't say, we cannot say that in general. But what if you looked at that long enough and tried to find the ensemble out of this? How hard would it be? Probably pretty hard, because you would take that as kind of mathematical identity and just assume it, and then try and find other things on top of that. Whereas in here in Haskell, they didn't have semicolons. They couldn't do this in general. How could they do it? And it took quite some time to figure it out. How far do we want to go into comonads? I'll draw two pictures, and then I'm going to call it good. Because the only thing I've learned is that everybody has to learn their own way. So I want to give you a general enough framework that you can go and attack these things and not be so scared. And trying to remove this idea that when you look at the maybe monad, you're like, what does that look like in the world? Is this a maybe monad? I can touch it. What monad is it? And it doesn't work that way. This is how I think of it in my mind. And my mind is not fun. So this is how I think of it. We have this space down here, this two-dimensional space, and it's the functions of A. It's all the functions that we're used to. So +1, 2 times x, all those pure functions that just do kind of mathy things. And then when I think of monads, I think of these things This is what they actually look like in my mind. Don't ask me why. We have this higher dimensional space of these M things, and notice the A's correspond. And when we work within a monad, what we're constantly doing is, we like all these guys. These guys are fun and interesting, and we know them very well. And these guys change and become different. We may have a M2, a B, and these guys are all floating above it. And what we're concerned with is, how do we get an A, how do we get functions out of here, and how do we get them in there? And that's the interesting bit. And that's where the monads come in. They give us the tools to take functions from down here and lift them in. Now the interesting part is that once you're in them, you're stuck. Once you've kind of ascended, and you've gone into one, you're stuck. You're there forever. You never get out. Now, does that sound like a bad thing? Yeah, I guess it does. But when we wrote our program out kind of on the horizontal stringification, spaghettification style, all stretched out, once we got into it, did we ever really want to leave it? We wanted that sequencing, right? So once you get into these things, it's actually kind of nice to be in. But what you do want to be able to do is, I had my g of x, he was down in this space, I wanted him to get in there. So I injected him up in there too. And then what was happening in here? It was saying, well, I'll run f first, then I'll run your g. Thus giving you your usual program, where it's kind of top down and nice and fine. So that's how I look at them. Did anybody learn something new from that? Maybe a takeaway. When you see these guys in action, you shouldn't be afraid. So how to pull it back to ensembles? We take the functions that we're used to and we make them not as important. So this is why when I see functional programming done typically, and there's an emphasis on functions are magical, functions are everything. Yeah, but that's not saying much at that point. It's much more interesting when you do get forced into monads. And you can program these anywhere. C# has them now, from what I've heard. I don't know, early closure, have they picked up at all?
But I'm still not sure what
JavaScript has some prominent ones, promises.
Yeah. What is a promise? Depends on where you're using it, right? There's a context associated to it. It's kind of like saying, what is a for loop? And this is like this whole philosophical, like.
Yeah, Java has futures, but they don't necessarily need to compose monadically.
Yeah, and we're skipping how we compose things. It's like a nice fallout, but it's not required. Actually, no, it's required asterisk, but we don't care. Comonads, where do they come from? The way I think of them is, if you don't want to get stuck in this, what if you want to get back down into here? But you want to do it in such a way that, and I did say on my little keywords that there would be multiverses, so this is where it's going to come in. Anybody that was looking for hard syntax, I'm sorry. We can schedule a talk some other time that's not general, and I can give you the nitty-gritty of this, and we can go into detail, but I don't think it's as important as people think it is. You'll run into these things called comonads, and they sound very scary. The whole idea is that they're kind of the inverse of this. They do everything backwards. So in the other space, we had all these nice pure functions that we can all write, and they go into these globular floating things, right? What if we wanted to take the globular floating thing that is specific to some kind of something, maybe, whatever, and we wanted it to create the A's, and create maybe an A prime, and create an A double prime, or upside down prime. What would that be like? That would be the comonadic effect, or feel, I should say. This is how I look at them. So in the context of real programs, if you ever encounter them, you'll usually encounter them in these things called zippers. And when you get there, they'll be very confusing because a lot of these really academic papers will say, it's just a comonad, blah, 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 and you get very scared and you run away. Don't run away, just mess with it, kind of work around it, like you did in 127A when you didn't know what an object was, but they gave you lots of objects, and somehow you passed the class, hopefully. I don't think we have any 127A students in here. We can't, right? Because it's not the first semester.
Well, what is a
It's still
basis?
offered though.
Oh, no. mind blown. But right, there was some point in your life when you just used objects, but somehow by the time students hit this kind of concept, they're at that point where they think they know what something is. And that's all they ever want from that point forward. You give them an idea, they want to know concretely, what is it? What is it like? What's it like in the real world? Or maybe it doesn't have anything in the real world that it's analogous to, right? The whole idea of analogies are deficient, kind of true. Comonads. Given a monad, they'll create these functional spaces down below. How many will they create? Infinity. Painful, right? Okay, last topic, I promise. What if we do this? Does anybody know what a multiverse is? The arrows are going the wrong way. What does it have to be? Okay, it has to be comonad. Now let me rewrite the name. Something universe-like. We can't interact with it. We're in it, but we're not interacting with it. What we are is we're down here. So this creates a universe. The idea is that up here we have something that creates a universe. It's kind of like this nebulous thing floating. And whenever we say, give us a universe, it gives us a universe. The problem, quote unquote, is that it gives us an infinite number of universes. Is that a problem? Why would it be a problem? Maybe you're in this one. Well, that's all you would know, right? When I said the functions, the plane of functions, that was all the functions that could ever be made. If this is all the U that ever could be made in this certain arrangement, would you ever know that you're not in one of the others, and would it matter? No, it doesn't matter. That's the whole concept of you are the center of the universe. What's outside of it, it doesn't matter if it's there or not. And this is the idea behind comonads. They create this effect. You'd have to take Haskell, kind of learn what lazy evaluation is, and then you would learn that infinity is actually easier to represent, easier to reason about programmatically than finite fixtures. And what does that feel like? If you have an infinite number of these function-like things, what are they forming? They're kind of ensemble-like, right? You don't care which one, you just know that you're operating within one. You don't care about the specifics. You don't say, I want universe 3. You stop worrying about that stuff. So hopefully I thoroughly confused you guys, but gave you nice pictures to think of if you ever encounter these in the wild. The takeaway is that they aren't things. They're groups of things, which will be very confusing because you'll hit very bad tutorials that were produced in my day. I'm sorry. That's just how we rolled back then. We didn't know what we were doing. We made lots of bad tutorials, and that always tries to show them as being things. We try and say it's a thing, and we equate it to, the popular one in my day was atomic waste in the ocean. And the idea is that back in our monad land, remember from the monad land, we have a singular space. We don't have any of the infinity here. We have infinity monads up here that we can work in. In that case, what we say is that this is atomic waste. And this is the ocean. Yeah. If you thought how I explained it was confusing, imagine atomic waste, spacesuits, and ocean. Why is that confusing? Because I know what atomic waste is, a spacesuit, and an ocean is. And trying to take abstract concepts and turn them into those, it's very confusing. What happens if you have a hole in your spacesuit and you're in the ocean with atomic waste? How does that relate to this? Nothing. Because it can't happen. I can't have a hole in my functions. There's not a function that I can't represent in my functional space here. So, don't be afraid to look at the more abstract. It usually helps. What other key points did I have? I think that's just about everything. Go forth, dive in. If you never encounter this stuff in your life, I can guarantee you will, but it'll be so abstracted and fixed that it'll be very consumable at that point. Remember, there was a time when functions were a programming paradigm. now we just take them for granted as being in our programming languages. But sometimes there were programming languages that didn't have functions. They were called subroutines. Yeah. Over time, this stuff gets kind of fixed and made available to everybody, so you don't have to think in this context all the time, because it does hurt your mind. It does give you C's in classes and things like that. So, all right, that's all I got. If there's any questions, for the people that really care, I'll go over an interesting relationship, but that's all I've got. Yes?
Do you have any papers to recommend reading?
Papers to recommend reading on the best paper to actually read is not a paper. Papers go a little too in-depth, unfortunately. If you feel that you can master this stuff, the papers that would be, the ones I would pick would be Wadler's original paper on monads. So this was 1991, 90, somewhere around there, right when they were coming into Haskell. And it's very interesting to see them derive this slowly in the paper. Like, it looks like a monad from math, but how can we subtly change it so it works to do I/O? That was their big thing. Actually, in Wadler's paper, it wasn't I/O first. It was building an interpreter, which is very sequenced, right? Do this, do this, do this, do this, do this. So that's what they wanted to do, and they were seeing common themes in there, and that's what he went over. And then more modern is Huey's paper on zippers. But that's going to be a really tough one to digest, because it deals with comonads, which are already pretty bizarro. You know, it is like the comic book Bizarro line. It's like the Bizarro monad. But what you can take from that is you can take the idea of zippers and go look at list zippers. And when you learn about comonadic effects in list zippers, it's much easier to reason about, especially if you're okay with lazy evaluation, infinite lists. If that stuff's pretty natural to you, these will be pretty natural as well. And then beyond that is Dan Piponi's blog post on evaluating cellular automata is comonadic. That's another really good one, because that one will probably set you up for reading the full tree zipper paper, which is pretty intense. But yeah, you just kind of have to Google around, read everything. Your set of things that will help you learn these will be very different from mine. But that's just kind of the state we're in at this point. Any other questions? Are monads important? Surprisingly, no. They're not as important as we thought they were. We know they exist. They explain a lot of things very interestingly, but they aren't the end-all, be-all. Maybe 10 years ago, we were kind of in the position of everybody will have to know monads in the future. You will have to know them. Now, not so much. Software breaks, right? We're not trying to construct provably mathematical software all the time. It's okay for software to fail. This could be expensive to write code in if you had to do this all day long. Imagine the people that you would have to hire to do this all day long. It's like a fraction of the programmers out there that can stand to do this all day long. So no, this is not going to be the thing that everybody has to know in like 10 years. Anything else? Yes, no? 2 weeks, I think I'm supposed to give another talk. So I am done with this stuff. I've done my 2 years worth of this stuff. I do find it interesting, but it's more in a playful context. More along the lines of like, what could you do with a quantum computer that's the size of a galaxy? And that's never going to get me a job. There's no job that has that as a requirement. Like, think of stupid things. But it is fun to think about. It is fun to know, because once you see it, you're like, oh my god, it's so simple. But it wasn't. It was like the path to get there was quite arduous and involved. And then you got there, you realized, and it didn't help you get a job, but it's fun to think about. So if you like games, you might like this stuff. If you don't like games, this probably won't be very interesting. That's all I got.